Okay, guys, what we're going to be doing today is something that we're going to be using for optimization, okay? And we discuss first, we're going to discuss first polynomials. Remember a polynomial looks like this, 3x squared plus 2x plus 4, for example. Right? So the first thing you need to remember, I will do something more. For example, let's say 6x cubed. We need to understand how MATLAB reads or R reads a polynomial. Okay, the way that we read how MATLAB reads a polynomial, this one here is degree 0, x to the power 0, x to the power 1, x to the power 2, x to the power 3, and then we write this in terms of a vector 3, 2, 4. So for MATLAB, it's going to be exactly this one here, right? So this is degree 0, 1, 2, and 3. Now, how do you think you can write 7x6 plus 4x4 plus 2x squared plus x? How do you think you can write this stuff? So you need to be sure that MATLAB understands that you are talking about. If I write this in this way, what do you think MATLAB is going to think?
Just a vector.
Yes, it is a vector, but do you think this is telling MATLAB that we have this polynomial here?
No, it's saying like 7x cubed, right?
Yeah, so it is basically, this one here is not this one here. This one here is simply, there's no way MATLAB recognizes that there is a power here. So for MATLAB, it's going to be 7x cubed plus 4x squared plus 2x plus 1. You see that? And this is not what we want. If we want to see what we have here, so we need to fill up with zeros. So for MATLAB, this is going to be 7, 0 for x5, 4, 0 for x3, 2, 1, and 0. You agree? So this 0 represents x4, x5, x to the power 5, x to the power 3, and my constant. So this one here represents this one here. Make sense? Okay, so can we enter this equation here? 6x cubed plus 3x squared plus 2x plus 4. So let's do this in MATLAB. Let me share my MATLAB. It's 6324. So what I will do is I will say A equals 6, 3, what was that? 2, 4, something like that. Yep. So this is going to be 6x cubed, 3x squared plus 2x plus 4. Right? Now, one of the things that we normally do is you want to find the roots. Remember what is finding the roots? If this equation, if this polynomial here equals 0, what you try to do is which values of x satisfy this condition that make the polynomial equal to 0. Okay, so if we want to do that, we can call that the command is simply roots of your variable. These are the roots. I have a third power. Remember, third power has three roots, correct? Now, if you want to go back, so if you know x, you want to go back to your polynomial, what you're going to do is let's call PP, and the command is going to be poly of R. Okay, so this is a standardized. If you take a look, guys, this one here is equal to this one here. If you just do PP product, PP times 6. So remember that it is what is called normalized values. Normalized means that they use the 6, the highest value, the highest polynomial, the coefficient that is with the highest polynomial divides everything, right? So that's why you have here 1, 0.5, etc. If you want to recover a complete polynomial, you simply multiply by the highest value, by the maximum value, not the maximum value, by the coefficient of the highest polynomial. Make sense to you? Now, we can also multiply. So let's assume, guys, that I have, let's do an array simply 1, 2, let's do 3 and 4. Okay, and let's have a b that is going to be equal to whatever. 1, 9, let's say 1, 4, just to make it easy, 9, 16. So I have I have two vectors, okay, or two polynomials, a and b. And what I want to do is I want to multiply them, okay? So remember, matrix multiplication, guys, is not equal to polynomial multiplication, right? So that's why we have a special command here, is convolution. Okay, this is the mathematical technique in polynomial mathematics is called convolution. Multiplication is called convolution. A comma b. And here we go. How do you read this one here, guys? What is this one here? What is this in polynomial terms? Guys, what is the, how do you write this in polynomial terms? What is 1 represents what? 1 is the coefficient of what? X to the power what?
Could be 7.
7. So this is 0. This is a constant. 1, 2, 3, 4, 5, 6. Remember, this one here is x to the power 0. So basically a constant. Makes sense to everyone? So it should be x to the power 6 plus 6 times x to the power 6 plus 20 x to the 5, 50 x to the 4, 75 x to the, wait, I'm wrong. 1, 2, 3, 4, 5, 6. Yeah, 6, 5, 4, 3, 2, 1. And x to the 0. Make sense to you? Guys, agree? Okay, now, when you want to sum two polynomials, so remember that if you want to sum, so if you want to sum two polynomials, so let's assume the first one was, so this was a, no? A was equal to x was 1, 2, 3, x power 3 plus 2x squared plus 3x plus 4. So this was a, and b was equal to x cubed plus 4x squared plus 9x plus 16. Do you agree, guys? This is our a and b. Then if I sum these two, if they are the same order, guys, it's very simple. It's simply 2x cubed plus 6x squared plus 12x plus 20. Got it? Now, however, if you want to sum something that is different dimensions, okay, in that case you need to paddle with zeros. For example, so let's do this first. Let's do MATLAB again, and let's compute. Let's call D. That is going to be equal to a plus b. Okay, so this is what I got. Now imagine that I want to where is D? What is the big this one here? Okay, so let me take a picture of this stuff here. Yeah. So if I want to sum this one here, let's say with this is C plus D. Okay. Remember that C was equal to what was C? C was equal to x6 plus 6x5 plus 20x4 plus 50x to the power 3 plus 75x squared plus 84x plus 64. Okay, so C was C. Now, guys, you want to do C plus B, for example, or, you know, if I want to do, yeah, C plus D. Okay, so when you do D, guys, in just doing this by hand, what you do is you put simply you just be sure that x3 goes with x3. So this is going to be x3 plus 4x2 plus 9x plus 16. Do you see? And then you simply sum. In order to tell MATLAB to do this type of operations, guys, of sums when you have different dimensions, what you need to do is you need to tell MATLAB, okay, I have 0x6 plus 0x5 plus 0x4 plus. So basically what you need to do, guys, you need to transform this one into a 0, 0, 0, 1, 4, 9, 16. Okay? And then MATLAB is going to understand what you're trying to do. Make sense? Okay, so let me do this here. What I will do is I will create E, and E is going to be equal to C plus, I will create D, yeah, let's say D. It's going to be, I need 0, 0, 0, and D. Can I do that, yes or not? You agree? And then if you do this, you obtain your result. Got it? Okay, guys, you do this. Please create an M file. Let's call it polyad. And it will have two, you need to enter two vectors, and then you are going to report something that is called P. And the only thing that this is going to do, guys, is going to simply sum. The objective is to sum two polynomials. Okay, but these two polynomials can be exactly like A and B, but also you can have C and D, for example. So your program should be able to paddle with zeros automatically. Right? So if A is like this one here, and B is like C, you need to be able to program, your program should be immediately able to paddle with zeros, one of them. Got it? Let's say 5 minutes to do this. And I will show you a couple of tricks there. 5 minutes, guys, to do this. Remember, guys, there is a command that is called zeros. Remember, so you can say zeros 1, 2, for example. It provides zeros. Okay, so this should be automatic. So the thing is that the dimension here, how many zeros you're going to be adding, that's the tricky part that you need to start thinking a little. Oh, you don't see that. I'm sorry. I need to show you my MATLAB. Guys, remember last class we did this command. It's called zeros. It's a special matrix. When I say zeros, this is number of rows, number of columns. So I create 1 row, 2 columns. I can create that. And remember, guys, that if you do, for example, zeros with a negative dimension, it doesn't do anything. It simply is empty. Right? So a couple of tricks. Okay, use these zeros to paddle with zeros in an automatic way. So you use size, length, whatever you can to create that.
I mean, Professor, we don't exactly need a zero beyond a 1 for the roll number, just because, I mean, it should just be 1 in the front, and then it's, you modify the second variable, right?
It depends. It depends on how do I give you what is A and what is B. So A can be the smallest one and B can be the largest. So you need to have two corrections.
Okay, got it.
Yeah. Two more minutes, guys. One more minute.
Yeah, Professor, I coded this like how I would code it in R, and surprisingly, it worked.
Sorry, Kevin, what?
No, I coded this like how I would code it in R. Surprisingly, it worked.
Yeah, should work. MATLAB is the same. It's exactly the same. Okay, one more minute, guys, and we solve this together, okay?
Slight differences.
Oh, yeah, it's like. Okay, guys, 1 minute, and then we solve it. Okay, so let me show you my program, and then we discuss, and then you tell me if what do you think? Do you see my screen? Do you see my MATLAB screen? Yes. Okay, so what I've done, guys, is I created P is going to be called polyadd. So this is my name, the function name. AB is going to be my input. So I need two vectors. Okay, and I will return P. That is going to be my output. What I'm doing here is a very simple check. I say that if number of arguments is less than 2, so remember the number of arguments, guys, counts these ones here, 1 and 2. So this is the number of arguments, okay? So we can run by pieces. Okay, of course, number of arguments here. In this particular one, sorry, in this particular case, it's going to be these two. I need to run up to here. Here. I don't know if I have A and B, first of all. I have A, I have B. Yes, I have A and B. So I need to run this one here from here. Remember, I cannot run this inside here because I don't have A and B. And then I will stop here. So now I can take a look to this one here. Number of arguments is 2. So remember, number of arguments means simply how many inputs you have in your input list. Right? So I have less than 2 arguments, no, so I can do the sums. And this is a trick, guys, that is very interesting. Do you remember what this one does? A, 2 points, A parentheses, semicolon, what it does, remember that? It simply transforms any vector into a column vector, okay? And when you do this dot transpose, So you first be sure that you don't know if this is like that or row or column. What you do first is transform everything to column, and then you put everything into row. So that's what this one does. If I transform everything into column, this one here transforms everything into rows. Okay, just to be sure. This is a small trick that I normally try to do. It works really nice. So I'm sure now that A is a single row and B is a single row. And then what I do, guys, is I play with the length. Take a look to what happens with my run. So what I'm doing is, what is the length of A is 4. What is the length of B is 4. Okay. And then what I do is a paddling. So I need to do double paddling. I need to paddling on A. This is my vector A, and this is my polynomial B. So what I do is I add zeros to the left of each of them. And how many zeros? Well, it depends. It will be zeros one row in both cases. And in this case here is going to be NB, so the size of the larger one. So if NB is larger, it's going to be NB minus NA is going to be a positive number. So I will have zeros here. And if NA is larger than, sorry, if NB is if NA is larger than NB, this is going to be a negative number. Do you agree? So, and remember that 0, comma, the arguments of 0 is a negative number. It returns simply empty. So it simply disappears. Got it? And the same here. So take a look to what happens. So I will do this a D here just to check. So let me move this, and then we're going to do another example. So you run. Cannot run from here again. Yeah, from here. You can see your P is this one here. Got it? Now, let's do the following. Let's do the previous one. I want in here, I want to add A and C. Remember, C is the one that has x to the power 7 or 6. I don't remember. Do you remember that? Okay, so let's try to take a look to this one here. So what happens if I do 2 that are not the same dimension? Oh, I don't have C. Oh, no. Yeah, where's C here? Yeah, I have C. But I will create this again. Yeah, okay, so now I should be able to do it. Convolution, sorry, not convolution. Polyad A and C. Make sense? So we can run. And here we go. Take a look. A is going to be like that. B is going to be like that. NA. So the first one is going to be the smallest polynomial, and the second one is the largest polynomial. So in this case, I need to paddle the smallest one, this one here. So how many zeros I will do? NB is 7 minus 4, 3. So I will paddle with 3 zeros. Do you agree? So take a look to this part here. You see, it paddles with 3 zeros. Now, what happens with the second part? What is this one here? Is 4 minus 7 is what? A negative number. So what is the zeros of when you have a position that is negative? It's simply empty. Oh, I can copy all this part. You see, there is empty here and works beautifully. Do you see that, guys? And then you simply run, and then you obtain your results. Here you go with your P. Questions?
Messed up a little bit on the matrix part. I thought, can you go back to the whiteboard for a second?
To the what?
The whiteboard.
Yeah.
Like we were right. Yeah.
Yeah, this one.
Yeah. Question. Just from an algorithmic perspective. So let's say I start with x3, x2. Okay, yeah, no, now I get it. No, sorry, I was confused. I thought it was the other way around. Add 0 to the 1. Yeah, because essentially I'm just adding 0 to the one that's smaller in length, right?
Yes, exactly. That's what you do.
Right.
That's what you do.
Yeah, so and then 0 is supposed to.
These zeros here represents the missing x's. So here, for example, I need to put 0 here because I'm missing x6 in this one here. Do you see?
Right, got it. Okay.
Okay. I will put this MATLAB just for you to, if you want to take a look for a minute. So we'll remove this guy here. I don't need this. You need to have this one here, guys, because we're going to be working with this one. If you can please type it very quickly. We're going to be using this one. 2 minutes to do this. Ready? Makes sense, no? Remember, guys, at the beginning it's kind of tricky, but you just try to ensemble your mindset, guys. Once you do that, you're gonna do your beautiful problems later. Okay, guys, everyone is here. And Jameson, you see that the use of nargin? So this is the way we use number of arguments. Okay.
Yeah, I understand that now. I did it differently before.
Yep. Yep. So it's basically counting these ones here. Okay, guys, can you please open the file that is called polyat1? I sent you this file today in the morning. Can you add polyat1? I will move this. Whoa, what I'm doing? No. What? Open polyat1, please, guys. Let's polyat1 here. I can add here polyat. Yeah. Okay, so I can put this next to this one here. Here we go. So can you take a couple of minutes to understand what is polyad A, B, C? So here what I will do is I will sum 3 vectors now, three polynomials, not 2. Okay, take a look to what happens. And what I will do, guys, I will call a function that is called polyad that we have created just now. So this is a function calling another function. Do you agree? Okay, try to understand what I've done here. And we talk in 3 minutes. And try to run and see how this works. Make sense? Okay, so what I've done here, guys, is simply counted the number of I want this to be more generic than just 3. You can do this generic as generic as you want later. What I'm saying is if number of argument is 3, okay, consider n equals 3. If number of arguments is less than 3, and number of arguments equal to 2, it's basically number of, I could have just written number of arguments equal to 2, n equals 2, otherwise error. Okay, because if I have only a single vector, I cannot do anything. Once I have this, then I say if n equals 2, okay, what I need to do, I simply need to sum two vectors, right? So I says the simple polyad. So simply my p thought is going to be polyad of A and B. Now, if I have a 3, because if it's less than 2, it simply collapses. If it's 3, what I will do is I will do two P1s. I do polyad, I compute P1, that is the sum of A and B. And then I do P thought, that is going to be simply the sum of P1, that is, this is 1, plus C. And then you have it. Makes sense? A very toy example. And then you can modify this using a for loops. You can do much more efficient program to run. Make sense? So we can run this from here. We can run this from here. So we can say, I don't know if I should have A, B, and C. Yeah, I have it. I have A, B, and C. Here I go. This is my result. Take a look if you get the same numbers.
One problem. How did the C get so big again?
Oh, because C is big. I think C is a vector that is a big vector. We created that before. I don't know. We created this C as, I think this was, C was a convolution of A and B. C was a product of A and B. Yeah. Okay, so let's create another, let's do now, guys, derivatives. Okay, so let's call G equals C. So just to work with this one here. Remember, this is 1, 2, 3, 4, 5, 6. So this is x to the power 6, 6 to the power 5, etc. Right? So if I want to make the derivative, guys, and we're going to use this one all the time, is polyder of G, and that's it. Make sense? So this is the derivative of G. So what is that? So let me be sure that you understand what I'm doing. This is C. Okay, what I've done, derivatives. So what I've done, guys, is, okay, I have called G is going to be equal to C. So it's going to be x6, 6x5, 20x4 plus 50x3 plus 75x squared plus 84x plus 64. Okay, so when I say derivative of G respect to X, that is simply equal to G prime. So I will do only the first one that are easy. It's going to be obviously equal to 6x5 plus 30x4 plus 80x3 plus 150x2 plus 150x plus 84, right, guys? This is the first derivative. So in matrix form, this is 6, 30, 80, 150, 150, 84. So it's the first derivative only. So you want to do this stuff, or well, sorry, you want to do this stuff. This is what is called polyder. Make sense? This is what I'm doing here. I'm doing polyder G, and that's what I obtain. You see that? 6 is going to be 6x5, etc. Questions, guys? Make sense? Now, guys, imagine that I give you the following polynomial. P is going to be equal to 1, 4, minus 7, minus 10. So this is a cubic, right? Now I tell you, can you tell me how this polynomial looks in the interval minus 1 and 3? This is one of the things that always caught my attention, guys, when I started doing economics, and we use all these functions, quadratic, cubics for a total cost function, etc. It's kind of weird to imagine a function, do you agree? Unless you start drawing a function, you can imagine, but MATLAB helps you, and R and Python helps you to more or less have a picture, how the function looks like, okay? Where is a maximum, minimum, etc. So for that, in order to create, what we do, guys, is polynomial evaluation. Do you agree? So remember, if you have a line, how do you draw the line? Well, you need just 2 points, correct? So you did this. What if x equals 0? What is the value of y? That's what we're going to be doing. Got it? So what we do is we simply replace the values of x in the equation in the polynomial, and then we have 1 point. Another value of x, another point, etc. Got it? So let's define my x, guys, as a linked space. I said from minus 1 to 3. Remember that if I leave this like this, how many variables in between I will have? What is the default in linked space? You remember?
Default is 1 increment, so -1, 0, 1, 2, 3.
No, the limit space, remember guys, it provides you a specific number of observations between two limits. The default is at 100.
100.
Yes, it will create 100 values, okay? So it will be okay. Now, if I want to do that, I want to evaluate my function, this P, using these values. Right? So technically what I'm doing is I'm saying, if x equals -1, I simply replace the x in my equation here, and then I have one value. Do you agree? Do you understand what I'm doing? Guys, do you understand or not? Okay, so let me do one example, because it's important to understand what we are doing. So let me create another one. I will do a simple example. So assume that y equals 3x minus 2. Okay? I want you to graph this one here. I told you guys, graph this line. So what you do normally is, okay, you say x and y. So normally I do, if I have x equals 0, y is going to be -2, correct? If x equals 1, so it's going to be 3 times x. This one is 1. And then from these 2 points, of course, I'm able to, if this is x is 0, y is -2. I have 1 point here. And the other one is 1, 1, 1, and 1. This is your point here. And then I simply draw my line. Correct? So what polyval does is this part here. So what you input is a series of zeros, then this a series of values for x, and these values are replaced one by one in the function to create this value here. Make sense to you guys? Okay, it's clear to everyone now? Yep. Okay. So now we can do that. So I will call B as polyval. I need to know the polynomial first, and then the values that I want to use for evaluating. Okay, I will not do the. I don't want to show the 100 graphs, but I want to plot it. So I want to plot x with B. And then you can add titles, you can add whatever you want. Here you go. Take a look, guys. Between -1 and 3, the function that is defined like this one here, the polynomial, the function.
Can see it. We can see
you
it.
cannot see the graph. 1 second. I need to change to this one here. Now, do you see that?
Yep.
You see, in -1 and 3, this is the way my function looks like. It's cool, right? Really, I really love this part here because it gives you a perspective of what you're talking about. Because for me, this is Chinese. I have no clue how. I know it's a cube, but I have no idea how this looks in a given interval.
So, Professor, just to clarify, the x value from -1 to 3 will essentially generate 100 of them. Those are essentially the x value going into the function represented by p, which essentially goes on write out as x times x to the third plus
Yes,
x
yes,
minus 10.
exactly that.
Got it.
Yes, exactly that. Exactly that. So each value, so the -1 is going to be 1 to the -1 to the power 3 plus 4 to the -1 to the power 2 minus 7 minus 1 times -1 and minus 10. Exactly that. It's 1 by 1. Oh. Okay, guys. Now let's start going into, we're moving towards optimization, okay? But we need to distinguish first between two things. One that is curve fitting, and the other one that is called interpolation. Okay, so basically, guys, imagine that we have data like this. So you have observations like this. Something like that. Okay, so this is my X, this is my Y. Okay, so what is curve fitting, guys? Is try to find a function that best represents the data. Okay, it's going to be a smooth function. Okay, one criteria that we use for curve fitting, for example, is my ordinary least squares, the very basic ordinary least square model. So if I do OLS model or curve fitting, my line, for example, the curve that best fits is one here. Perhaps it's going to be, oh, sorry, something like that. Assume. Now, what is interpolation, guys? Interpolation, no. Interpolation uses every single value of the observations and then tries to find what is the best way to go from this point to this point. So basically, what it will do is we'll try to do something like that. You see, something like that. Okay? So interpolation, and normally what we use is linear interpolation. So if I go from this value to this value, what is the value in between? It's simply a proportion of values. Okay? But you can do cubic interpolations, etc. So that's the main difference. Curve fitting implies that you're using a function, you're using an econometric model, or a statistical model that tries to represent the data in a smooth way. Meanwhile, interpolation, guys, is simply trying to select every single point of the observation and tries to connect with the other points in the data. Got it? So,
Professor, can you, the interpolation is something covered extensively in Professor Shaw's class, but can you,
yes.
in your word, kind of conclude why, in your opinion, interpolation is important?
Why interpolation is important?
Yeah, in your words.
Yeah, well, interpolation is important because what you try to know is you try to see the dynamics of moving from one point in real data, the dynamics of how do I move from this point here, let me my pen, to this point here. This is important. In the curve fit, you don't have that. You have a smooth function of that, and sometimes you're not interested on what is my value of X and what is my value of Y in average. You don't want that. What you want is that dynamics of moving from this point here to this point here. For example, when you do macro with the shown, what you're always interested is about the equilibrium situation. So how happens when I'm in situation number A if I raise taxes, for example? Okay, from 21%, I want to raise it to 28%. So what is going to be the dynamics of my, how much money I will recover from taxes? How much money I will get from taxes from here to here? Right? That's interpolation. It's moving from one point to the other point. That's crucial. But that's a different mindset. The other one here is simply going to tell you the average. So in average, if I move from X equals 1, for example, to X equals 1.5, in average, this is what happens. It's given in the red line. Make sense, Kevin?
Got it.
Great. Yeah, macro guys use a lot interpolation, but normally they use cubic interpolation. I know Sean what he used, but okay. Where is my? I don't know what happened with my MATLAB now. Oh, here I go. I don't know why I lost my MATLAB somewhere in this space. Okay, here we go. Do you see my MATLAB, guys? Yes. Okay, so let's create. I will create something. I will do. Let's do X equals 1 increasing by 0.1. Let's say to 1. So let's do from 0. Okay, so I have X. If you take a look. And then I will create these values, okay? I will create Y. Be, let's say 0.447, 1.978, 3.28, 6.16, 7.08, 7.34, 7.66, 9.56, 9.48, 9.3, Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 observations, 11 observations. Okay, so
Yeah, Professor, can you paste that very specific numbers to create it
yeah,
very
yeah,
quickly?
yeah. These are random numbers. Yeah, but better if you have these random numbers with you too. Where I do this? Where's my? You know why is going on here, chat? Yeah, you can paste that. Yeah, I send you these numbers, guys, in the chat. So we can do a plot XY just to take a look. Oh, I don't want this plot. I want plot XY. Yeah, you see, these are the points. You see my figure, guys?
We see one very large graph and with no code.
Ah, man. Yeah, so let me, I think this is the one that I need to share. Now, do you see this? You see both? So what I've done is plot X, Y, just dots. This one here tells me that I want to, tells MATLAB that I want to do dots. And here we go. Okay, so now what I want to do, guys, is I want to fit this one here. Okay, and what I will use for this one here, guys, I will call, let's call this P, and it's going to be polyfit is my command. What I want to polyfit X, Y, and N is going to be the degree. So 1 is linear, 2 is quadratic, 3 is cubic, etc. Okay, so let's create P that is going to be polyfit X and Y, polynomial degree 1. And this is this one here. So I have a polynomial. So how do I add a line to this graph here, guys? I need to evaluate, right? I need to create a polyval between 0 and 1. Agree with me, guys, or not? Okay, what I will create is I will create another xi just to make it more precise. It's going to be lim space, and I want to go from 0 to 100 observations. I have my P. So what I want to do now is Z, for example, and I want polyval. I have P, and I want to use the values Xi. Do you understand what I'm doing? So I'm taking the polyfit. So I'm fitting the function. So I have a polynomial. Now I want to put this polynomial in my figure, in this figure here, that are only dots. And for that, I need to create a polynomial. I need to evaluate my line in different points. Okay? So that's why I'm doing Z polyval X of Y. And then I can basically, guys, if I want to keep the same figure, not disappear the same figure, guys, I do hold on, remember? Remember, hold on is will print the graph in there. So what I will do now is plot Xi, Z, sorry, and I want this to be red. Here you
Professor,
go. Yes, Jameson.
for the polyfit command, what is the third input?
Oh, this one here, 1 is linear. So it's going to be this one here. Remember, this is my line. Do you agree? It's going to be 10.31x plus 1.34. So this is the equation of the line. So this one here gives me the degree of the polynomial.
Okay, perfect.
Okay, now guys, you yourselves create another one, do another polyfit called PP. Okay, just to keep everything continuous, create another polyfit PP, but now I want a degree number 2. So I want you to fit a quadratic function. No, yes, a polynomial degree 2. Do the same and graph in the same graph.
Professor, is there a limitation on how many degree I can go up with the?
Yeah.
Oh,
no,
okay, cool.
Technically no, but however, what you do is you create overfitting. Let's do one example. So finish 2 guys. Let's do the graph. Let's analyze the graph, and then we can do 10. And you want to see, that's a problem of overfitting. You want to see how terrible what can happen with an overfitting.
Question about a definition of overfitting. Just in the context of machine learning of what I do know, that really just means you have a very high accuracy rate, right? With
Yes, but it's not good for forecasting.
yeah.
Of course, as in neural networks, for example, the more the neurons, the more precise is your replication of the past. But try to forecast the future, it simply is terrible. And you're going to see in a couple of minutes why.
Noted.
Yep. Okay, so if I want to do the polyfit second order, it should be fast, guys. So I will call this 2, and just to keep the P, I will call this PP. Right? I have a quadratic equation now. Then I can do let's call it C1. Right? I'm using now PP as my polynomial, and xi is the same x values. And then I can I continue in hold on, so I'm okay. So I will do xc1. And I want this to be green, perhaps. And then we can see the figure. You see, the quadratic goes like that. Guys, make sense to you? Yep.
Yeah.
Okay, now let's do an overfitting. So assume n, so my polynomial is degree 10. So you can see here, guys, I believe that the second one is much better. We're going to do more when you do OLS regressions. You're going to see that. but the second one represents better the data because there is a kind of a break in this part here, right? That the line is not able to really capture, but in any case. But now you say, oh, you know what, the second is better, so let's do 10. And if you do 10, what happens?
Oh no, that's horrible.
It is. It is really terrible.
That's not good at all.
No. So let's do 10. I will call this PPPP. Okay, so you have a 10-degree polynomial, and I will create C2. This is PPPP. This is going to be C2. And then I do my I've already read that, so I need to just plot xi z2, and I can call this what? Black, perhaps? Oh, blue, sorry, B is blue, it's not black. You can see, guys. You see? So it looks more like, not even like interpolation, because interpolation is from this point to this point. So this really is trying to force a function to fit in a given interval. So the results are can be really catastrophic. Okay, so you know how to do derivatives, you know how to evaluate a polynomial, you know how to run this type of graphs. So let me now move into some of the interpolation that I was planning to move on that, but let's do it, because indeed the macro guys use this one here. Let's create let's create two variables. Let's do linear interpolation first. Let's do x1, and let's do a linspace. Just let's create sine function 0,2 times pi and 100 observations. Okay, so let's create x1 and let's create x2. Oh, not 2. Yeah, and I want only, let's say 6 observations. No. Yeah, let's call this 2x2, otherwise x2. Okay, now what is beautiful about interpolation, guys, is that the more data you have, the better your interpolation. Got it? Let's take a look at what happens. I will plot x1. Remember, x1 has 100 observations, and I will plot sine of x1. So this is my first my first pair. In plot, I can do pairwise. I will plot x2 with sine of x2, and I can do this perhaps something like that. So plot, guys, you can do as many plots xy pairs as you want. So, but you need to put them in pairs. So this is going to be x1 sine of x1 is the first pair, x2 sine of x2 is the second pair, and I'm giving the second pair to be dashed. Okay, take a look to what happens. Look, the blue one is the one that has 100 observations, and the red one is the one that only has 6 observations. You see that? You can see the fit. It's not so good. That's why in linear interpolation, guys, the better is to have the most data. So more data is beautiful. Okay, let me write. So let's do hours 1 to 12. So I have 12 hours in a day, and I will call temperatures, and I will create simply, these are daily temperatures, okay? 5, 8, 9, 15, 25, 29, 31, 30, 22, 25, 27, 24. How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. So we'll give you this. So assume, guys, these are the temperatures on a given city. Okay, so you have it here in the chat. And that's normally one example. Temperature is one example that we use a lot in linear interpolation or cubic, later we're gonna see. Okay. So 6 hours. So this can be hours, for example, from 6 in the morning or perhaps midnight up to noon, something like that. Something like that. 12 hours of data. So let's do a plot. Let's delete this one. I don't need this plot anymore. Let's do a plot, guys. And I will plot a lot of things. I will plot hours in the axis, temps. Temps. I will do hours again. Temps, and I will put here a plus just to you know, this creates these pluses in the points, just to have a more clarity.
Prof, just for a record, you're not actually doing interpolation here, right? You're just showing what interpolation could look like.
Yeah, no. Actually, plot is always an interpolation. The plot command always interpolates.
Oh,
okay, but now
automatically
automatically. That's the same in R. The plot command is exactly that. That's an interpolation. This is by default. Got it? So now let's try to understand how this works. So let's do, guys, the command for interpolation is going to be interp. It's going to be interp1. Okay, and then what you enter is your x and y. So in this case, my x is hours. How do you call it? Temps. Yes, temps. And then, just say, for example, at 9.3. So this is hours. I don't know. 0.3 of 1 hour is what? 920. Okay, so the command is going to be interp1. And here we go. So at 9.3, so 9, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So a 9.3 is between 22 and 25. Do you agree? So according to the interpolation, guys, at 9.20 is going to be a 9.20 is going to be 22.9. Okay, so now interpolation works also with intervals. So you can say, for example, what is the temperature at 3.2, 6.5, 7.1, 11, for example. Okay, so you can find interpolation of different hours, for example. Make sense? You can also, guys, there is another interpolation. So let me do 9.3 again. There is another interpolation that is called spline. Okay, spline is cubic interpolation. You can see it's not exactly 2290, it's 2185. So what it will do is it will do a curve. Okay, and let's take a look to more. It's the same. You can work with the previous ones. And by default, guys, splines is the one that we use all the time in economics. It's more, oh, what happened?
Professor, you type splines, not spline.
Yeah, you're completely right. Here we go. It says something wrong. Okay. So let's take a look to how this looks. So what I will do now, guys, is I will create another H1 that is going to be equal to 1 increasing by 0.1 to 12. So I'm creating a new series, more detail. I will create T that's going to be I will interpolate hours, temps in these intervals, and I will do an spline. Oh, you can copy there. I don't need to print. And now what I will do is I will plot hours, temps. Then I will plot H with T. Hours. Wait a second. So I want hours and temps. Yeah, I want perhaps this one to be like that. I want hours and temps, perhaps plus, and then I will do H comma T, just to see all of them. Okay, so the first pair is simply going to be the line, so the linear interpolation. This is linear interpolation. Our stems with the dots are simply the dots, where the dots are going to be located. And this one here is my spline, my cubic interpolation. So you can take a look to everything.
H1, not H, it's H1.
Yes, it's H1. Here we go. Here we go. You see that? Instead of the line linear interpolation, that is the kind of dots or dashes, the cubic spline is a smoothest function, you know, it's more smooth. And the one that we use, guys, and you're going to see why, when we talk about derivatives, remember that the worst case scenario is to take a derivative in a corner. Do you agree? What is the derivative of function in a corner? It doesn't exist, correct? That's why when we try to do mathematical models, we prefer a function that looks like that, because there are no kinks. There is always a function that is a curve. So this implies that every single dot has a slope, meaning that it has a derivative. Got it? So that's why splines are much more preferred in economic modeling, guys. And then you see it represents, yeah, you know, quite good. Okay, copy this one here, guys. And do you have questions? Please ask me questions.
Yeah, question. So just to reveal what I learned from my from Professor Shaw's class in financial econometrics class, is that essentially the purpose of interpolation is that when we take derivatives, we want to be able to take more derivatives than less. And because of the more derivatives we're taking, the graph will look less coarse and become smoother, and indicate we have a higher level of accuracy when it comes to forecasting.
Completely right.
Because we have
completely right.
Artificially created many values in between the existing values that we were given.
Yes, that's completely right. The thing, remember, guys, when derivatives, mathematical definition of derivative in a kink is infinite. So what is the slope? What is the slope in this point here? Infinite. There is basically, you can move a line like that, right? But what is the slope in a curve? So what is the slope in this point here? You can find it. In this point here, you can find it. In this point here, you can find it. What is the slope in this point here with a cubic spline? You can find it. Okay. However, if you are coming with a green line, you see that there is a kink here. What is the slope here? We have no clue. Got it? So that's why we try to smooth the function to find as many derivatives we want. And you're going to see later when we do utility functions, you're going to see how this works beautifully. Okay. Make sense? Okay, so I think that we can do now. Yeah, guys, up to here you can do the sixth assignment. Okay, the sixth homework. I already sent this to you. We're going to take a look later to that one there. That is a very interesting assignment, guys, because you're going to be polyfit, you're going to derive, you're going to do graphs, you're going to do a bunch of things. So that this number 6 is going to be one of the homework is going to be a kind of more challenging but more interesting, because now you're going to be optimizing, you're going to be finding trends, seasons, etc. Right? And you are able to do that now. You have all the tools to do that, guys. Okay. Okay, so let's do very quickly something that's called numerical analysis that we're going to use a lot in symbolic mathematics. Okay. So there are some commands, guys, that are really cool to have. Okay. So we have, for example, fplot. There is a function that is called humps. There is pre-built function, and I want to test this in the interval 0, 2. So humps, guys, is an example of MATLAB. Okay, this is a function. It's already built-in function that looks like this. Okay, so the command, yeah, what this one is telling you guys is that the next versions, this one here is defined as a string. Do you agree? Because it has apostrophes. What it's saying to you is that in the future, this is not going to be working like this, right? So I think that in the future, we are going to have the add function. We don't need to do this now, but just to let you know, you're going to replace the apostrophes, but an add function, and then you're going to get the same. This is still work in progress, guys, because the add gets very complicated when you have more than one variables. For example, you have X, Y, and Z. So then it gets a little fuzzy and complicated. So that's why MATLAB at this point continues using the humps like that. Okay? Just for you to know how this is going to work in the future. But for now, let's keep this one here. So the way it works is fplot means function plot. I need to define my function, and this is the interval. I want you to plot my function between 0 and 2. Okay, so we can do another function, another function. Let's define a function, for example, that is 2 times exponent of minus x sine of x. I'm just creating whatever function. Okay, and perhaps, yeah, you know what I will do just to make it easier. I will define this as f. And then what I will do is fplot instead of humps. Fplot of f, for example, in the interval 0, 8. Okay, so we have, this is my function, my fplot. So this is a 2 to the exponent minus x times sine of x. Looks like this in the interval 0, 8. And I will use this function, guys, because I have clearly a maximum and I have clearly a minimum here. We're going to use that to optimize here. Make sense? So we can create another plot directly in the fplot. I can do fplot. I don't need to do the f function, so I can directly write here. I will do x to the power 2 minus 2 times x plus 3. So this is my function. And I want to evaluate this one in the interval of 0, 3, for example. You see? So the fplot, you can write directly the function in here. This is the old version. So if you see the old version, looks like that. So the graph looks like that. Now in the new version, guys, if you want to do this one here, this is easy because it depends only on x. So what you do is add x. Add x. So your x is your variable, and then you simply define your function, and then you do it. You see? Here we go. Make sense? And you see all these comments here, guys? Yeah, this is why MATLAB is not able to release this new version yet, because there is a lot of comments, problems, functions that are not working properly, etc. Because this is a major change in MATLAB, and this is appearing, guys, from 2017, I think. This one is a really major change on MATLAB, and this one here is going to be able to link. It's going to be, once this is done, it's going to be fantastic, but at this point, it's not yet ready. Okay, guys, questions? Make sense? The fplot is a function that really quickly shows you your function. You can do the polyval, etc., but this one here is much simpler. So now let's do optimization. So I think we are ready for doing some optimization. Do you have questions up to now? Okay, we have normally, guys, in general, we have three optimization tools. We have something that is called a F-mean bounded. Oh, F-mean bounded. We have something that is called a F-mean search. And then you have something that's called a F0. Okay, the F-mean bounded, guys, finds the local maximum or minima. So this one finds local maximum or minima for a single variable. This one here is the same, finds local maximum or minima for for several variables. It can also work with one. And this one here, guys, finds positions, values, where the function crosses zero. Crosses zero. Okay, so imagine that you have a function, this is my zero, that crosses like that. It basically finds this value here. Okay. So remember also that imagine that you are finding the minimum. Okay, so a function. Sorry, let's do this differently. Imagine, guys, that you have a function that looks like that. Looks like a F distribution. Okay, it looks like that. Now, if you see, guys, all the functions always is going to be in terms of minimums. So how do you find the minimum if I want to find the maximum? I want to find the maximum, but I have only functions that do the minimum. So what do you do? What mathematical trick do you do? How do you invert this function?
You set everything to negative.
Exactly. What you do is you multiply by -1. Everything. So the function is. So if you invert the function, so this means multiply by -1, what you are going to be creating, yeah, it should be the same, okay? They doesn't look the same. But basically this point here, okay, is going to have a negative number. So imagine this is -7. Indeed, if you're looking at maximum, this is going to be equal to 7. Okay, so that's the way. Make sense? So you don't need to duplicate. You don't need to have x max bounded, etc. You simply reverse the matrices. No, not the matrices, the functions. Make sense to everyone? Okay, so now what we can do, guys, I think that the most efficient way to do that is I send you a lot of programs. So let's read them. So you are going to be investing 5 minutes or something like that to read the programs. And can you please find that, open the file that is called xfmean bounded? Do you see that? This one here. Example f-mean bounded. And I have created tons of things in this one here. But guys, please understand, 5 minutes to work with this. I have created more things in here, guys, just to show you something. But try to understand what I'm doing. Try to read. Okay, 5 minutes to do this, and I come in 5 minutes. Yeah. Do you understand that the functions? Make sense to you? So, okay, so let's do what we are doing here. Let's do it step by step. So we can stop here for a minute. And there is something that I need to show you here. Here, good. So look, guys, Fn is I'm defining my function. Okay, so this is the one that goes up and down. So it has a clear maximum and minimum. Then I will find the minimum, the F-min bounded of Fn of this function here in the interval 2 and 5. And remember, what I'm finding is x. Once I find x, what I do, I replace this one in my function, and then I have the y, correct? And what I have done here, guys, I have created this function here is a function in a function. So I could have created this one here as a completely independent function that, like the ones we have been working with. However, MATLAB, guys, has a possibility of creating functions inside the same function. You know, this is one function. When it finishes when it finds another function. So this function here is another function. Got it? And this function finishes when it finds another function. So how many functions do we have here? We have 3 functions in a single function. Make sense? You can do this. You can move this one here in the independent scripts, and you can do that also. It's exactly the same. So what I'm doing here is I find x first. So let's run up to here. I have my f plot. So this is my function, right?
Oh,
Agree?
can't see it.
Oh, again, let me see. Yes, this one here. You see now? You see the graph?
Yep.
Yep. Okay, so what I'm trying to find is the minimum. So it should be around this point here. Okay, so let's click here. Let's continue. So what is the x value? 3.9270. So indeed, it is around 3.92. So it's around here. Now, what I need to know is what is the value of y. So what I do is I import this value here into the function. This value gets exported here into this function and simply replaces the value of x into this function here, and then you have your y. Agree with me? Guys, do you agree with me? So I got x, then I use this x in a function. So this is the input for this function that is called find y min. So this is going to be coming here. This is 3.92. And this 3.92, what do? You simply create y that is going to be to the minus x. When you find an x, you find by the 3.92, and then that's it. You have y and return y that is going to be called, in this case, y min. Take a look to what happens. So my y min is minus 0.0279. Okay, so this means that my pair here is minus 3.92, I think, and the minimum y, so it's a negative value that goes to 0. What was the value? 0.0279. Make sense? Now I will plot what I'm doing here. Well, I know I can create a new figure here. I'm plotting Fn in 0.3. This is another function. No. It's the same function, guys, but plotted in a different interval. See, now I'm looking in the interval 0.3. Oh, yes, because I want to find the maximum. Okay, so what I do, guys, I simply change Fn just to find the maximum in this interval. I cannot find the maximum with a function. I need to find the minimum. So what I do is I do a minus to everything. Well, in this case, it's a product. So it's minus this. You do the same. And then that's what you get. Take a look. Perhaps I can do this here. Your x max is going to be in 0.78. Okay, what I've done here. Yeah, I need to close all these ones here. I will run everything again. So it is 0.78 here. What I need to know now is what is the value of y. Okay, so I have my x max. I will continue running. So my y min is my y max is 0.6448. So basically, what this one here is telling me that my max is in 0.78. The coordinates are 0.78. That corresponds to a y of 0.6448. Makes sense to everyone?
Can I just verbally walk through this algorithm very quickly? Just for understanding purposes.
This one, of this one here.
Yeah. So,
Yeah.
for the second part. Oh, okay.
Yeah, the second part. The
Yeah.
second part, guys. You know what I'm doing is this function. I'm evaluating in a different position, in a 0, 3. Okay. When I know that when it's 0, 3, I have a maximum. Right. So what I'm trying to find now is this maximum. The function is the same, guys. You can see the function is exactly the same. However, in order to optimize, in order to find this maximum, what I need to do is I need to transform the function. I need to revert the function, correct? I need to invert the function. The word is inverting. I need to invert the function.
Yeah, got it.
So that's why I'm doing the minus here. So remember, the original function is plus here. What I need to do is I need to invert the function, so minus. Then when I plot fn03, so let me do this, okay? Just for you to show you. You see, this was my maximum before, now it's my minimum. So that's what I've done when I revert this function. And then I find x max is the function f min. You can take a look what is x max here. Well, I already exit the function. So I can do this. You see, x max is 0.78. Basically, this is good. Let me move this here. Move this here. Yeah, you see that one is the mirror image of the other one, guys. You see that? You see? So finding the maximum is exactly the same as finding the minimum. When x is 0.78, you see? What is the value of y that maximizes? Is going to be, well, I need to run this again. Y is going to be 0.6448.
Yeah,
and there we go. Perfect. Guys, questions? Do you understand how the f-min bounded works? We have a single variable. It means that I only have x here. So I use f-min bounded. It's pretty efficient. F-min bounded is one of the most efficient optimizers that we have. Unfortunately, it works only with one variable. Okay, so that's why we have the other ones. Okay, questions? Okay, so we continue moving. Can you please take a look to this function, x f-min search. Let's use 5 minutes, guys, to analyze and understand this function. So remember, f-min search works with many different variables. So you can have x, y, and z, a, b, c, d, e, f, as many variables as you want. F-min search is the one to use. Okay, please analyze the example 5 minutes, and then we continue. Recording. So you can continue, guys, with x0. What I will do is I will explain this function again. So we have 3 variables. Just to complete our recording, okay? We have 3 variables. My function b has x, y, and z. So, and what we are going to do is we're going to have starting values. The function to find for minimums when you have more than one variable is f-min search. These are the functions that I've created here. It starts with the starting values. So 0.6 is going to be x, minus 1.2 is going to be y, and 0.135 is going to be z. And this program starts basically minimizing, trying to find what values of x and y and z minimize this function. And then finally return a that corresponds to the values that are minimum. Once you have this a, you replace in this function that calls eval_fun. And then you find your minimum, the values, the minimum value of your function that we are under study, that we have under study. That's it. Okay, guys, now you can please go into the f0 function. Remember that this function, what it finds is what are the points that crosses 0. Okay. Okay, 5 minutes to study this one here. please remember me to. Okay, so questions, guys, about the x0 function xf0.
Yeah, Professor. I'm
Yes.
a bit confused with how you call other functions in the same program. So how come you write at f in maybe line 13 or line
Yes.
16? It looks like the function would be called y.
Yeah, wait. Yes, let's do this by steps. If you have a function already defined, okay, the sine is a function that is built in MATLAB. Do you agree? Sine, cosine, tangent, etc. You use add the function. So if I think we define here a function. Yes. So here we define the function below. Do you see that? But the way to tell MATLAB get this function is the add command. And also here, I think we created a function. No, we haven't created here a function. So here I don't need to use that. But when there is a built-in function, or you are going to optimize F0, F min search, F bounded, and you want to link to a function that exists below, or a function that already exists in MATLAB, that the way you tell MATLAB, hey guys, use this function, please use this function, is at name of the function. Got it? So for example, here what I'm saying is give me the values of sine of x that cross 0 in the environment in the neighborhood of 3. That's what we're saying here. Okay, so let's take a look. Let me move this one here. 3.1416. So remember just to remember how the sine function works. So remember that trigonometric functions, sine, cosine, are very particular. Do you agree? So this is pi. This is 2 pi. This is pi over 2. 3 pi over 2. And then my sine function, so this is 1, this is 1, this is minus 1. So the sine goes up to here, comes here, goes to minus 1, and goes to 0. So this is the sine function. Do you remember that? And the cosine function, guys, goes this way, goes here, goes to minus 1 here. Then this goes up and goes here. So this is a cosine. And this one here is a sine. Agree? So basically, what we're saying is tell me that the value of the function sine that crosses 0 in the environment of 3. Where is this point? 3.14. Got it? That's what this part is telling us. Do you agree with me? 3.14 is basically where the function crosses 0. We don't need to compute y because we know that y is 0. That's when it crosses to 0, correct? Okay. Now we can do the same with cosine function in the range between 1 and 2. So let's take a look at what happens. Well, it tells me 1.57 that is equal to pi over 2. So the cosine equals 0. Cosine equals 0 here, pi over 2. Do you see that?
Question.
Yes.
What is the point of having a function that searches for a 0, even if you still have to tell it where to look?
No. You can put this in a very, very range. You can do 1 to 10.
Okay, so got it. So this is to maximize computational time. Got it.
Yeah. That's it. No, it will give you all the value that you want. Okay. Now this is interesting. What is f here? There. Because here I'm calling f. Do you agree? This f is not a function built in MATLAB, so we should have created this f function here. So where I have created this function, I have created this function down here. You see? So y equals, remember, the name of the function is this one here. correct? And this function needs as input x or any input. Remember that x can be any number, so I can have my function can call it x, but I can call it here if I want z. I can call it whatever I want. Right? And then we'll return y. That's what I'm saying. So here what we're saying is, okay, f plot this function in the interval -3 and 3. Okay, title, blah, 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 so it doesn't matter. So let's take a look to what happens. This is my function, guys. This is my f function. It's a cubic function, you see, and looks like this. Looks like a cost, no? A total cost on micro. Okay. Then what I'm doing is tell me when the zero is around here. Okay, tell me tell me the exact value of x when it crosses 0. So it should be around this point here. That's what I'm saying here.
Prof, we can't see the graph.
Give me 1 second. Yeah, here we go. You see the graph now?
Yep.
Yes. So basically what I'm saying is give me the value of x that when the function crosses 0. And I'm giving them a hint around 2. So it will be around here. That's my f0. My function is defined in this function f that is here below. And then you can run and tells you. So the value is 2.09. So if you see the graph, 2.09 is basically very close to here. And 2.09 somewhere here. Well, somewhere here. And the value here is here. You see? Now, this is another thing that is really cool, guys. Sometimes you have functions with specific coefficients. Okay, so an a is given, so you provide that. So for example, cosine of 2x, I want to do a cosine of 3x, I want a cosine of x simply. So this a is given by you. So I decide to do a 2, so this implies I will be computing cosine of 2x, okay? Okay, so I will plot, this is the way I'm calling the function. Sorry, this one here, guys, means the following. My plot, my variable in my plot is k. This is at k. Okay, so my variable in my plot is k. What is the name of my function? My function is my fun, and I need k and a. And the values that I want to be looking at is between 0 and 4 pi. Okay? So what it will do, so k, guys, are these values. So k is going to be between 0 and 4 pi. A is equal to 2, so these values come here. And what MATLAB does is simply starts running, and finds, and plots the function. Simply plots the function. So what is that? Okay, I never appear that. So this is my function. This is my cosine of 2x, you see? And then what I want, guys, now is to find the value when x crosses 0 around 0.1. That's what I'm saying. Just run 0.7854. Basically, we're saying that when this crosses 0, this point here in x is 0.7854. That's all. This is a way, guys, in which you can use variables that are fixed numbers. Okay? Normally, we use this in seasonality, sine, cosine, etc. So we want the number to be fixed, one number to be fixed, this one here. And so you simply enter here, but you need to tell MATLAB. If you don't tell this to MATLAB, guys, it will try to optimize between k and a. And we don't want that. A is a constant, and the only one that we need to maximize, or to, optimize or find a 0 is based on my function k, based on my value of k, my variable k. And that's it.
Question on the last line there. K equals to F0 at K, my fun KA. I get off that and then point 0.1. Why is that? Why doesn't that 0.1 needs to be there?
This one here? Oh, because I want to be close to 0. So in my graph, I want to be around here.
So that's essentially telling the graph, okay, I only want the first.
Exactly. So if you put, for example, from 0 to 12, you're going to have a bunch of points. You're going to have this point, this point, this point, this point, this point, all the points here. Make sense? Okay, guys, questions? No questions? You need to review this. So you have the weekend, guys, please review this part here, okay? It's very, optimization is something that we do all the time. You're gonna see. Okay, so don't stress because the first time looks like Chinese. So don't worry about that. It is like that. Yeah, here, let me know now, let me move now, guys, into something more. Go here. Yes. So now, guys, what we are going to be doing is what we do, integration. Okay, so we are going to start integrating. Do you remember? Let's do an F plot, humps, and then perhaps we can integrate this in what interval? Between -1 and 2. So just to remember how this function looks like. The function looks like this. Okay, and then what I will do, guys, is what is integration, guys? What do you do when you integrate between one point and another point? What are you doing mathematically? What you're doing is you're finding an area, right? That's what you do. Integration is simply finding what is the region or area below the line. That's what you do. Make sense to you? So let me be sure you understand this part here. When you integrate, when you do integration, guys, integrals. Okay, so I will try to replicate my function. It's going to be very tricky, but in any case. So I have my function that looks like that and something like that. Do you agree? So if I take an interval between A and B, so what I'm doing is what? I'm simply finding this area here. That's what I'm doing. Okay, so this goes up to here. That's integrals. Okay, so it's simply what is the area below, between A and B below the function. Okay, that's integrals. Now, in integrals, guys, the basic logic is what? How do I create this region here? When the easy or the first way of doing that was simply to create thin rectangles. You know, thin rectangles. Many rectangles. And then you simply compute, and then you sum all the rectangles, right? Because you can know the area of a rectangle, base and height, multiply n times, and then you get your area. What is the problem with that, with this method, guys, is that you have this part here that is extra. And sometimes there is less parts, and not all the part is going to be included. Do you see? So you have misses and you have pluses here. So, but let's do this one here first in MATLAB. So let's use the humps. No, that's fine. Yeah. So let's create, guys, the following. So let's do, let's do x from -1. Let's increase 0.1 to 2. Okay, I want to evaluate this, y equals humps of x. So I'm simply evaluating y, so I'm finding x and y. And I will do, yeah, I've done the F plot already, so you know the F plot. And I will do simply the area. This is a name, and it's going to be trapezoidal x, comma, y. So this is the function. So trapezoidal, guys, basically what I'm doing is small. So my rectangles are going to be these ones here. Okay, so that the size of my rectangles are going to be 0.1. And then I simply find that the height is given by y. You see? So the area of the rectangle is going to be the base and height. And then I multiply as many variables as I have, and I have it. So basically, guys, the area of the humps between -1 and 2, if I have rectangles of size 0.1, equals 26.46. Now, of course, if I do thinner, bases, the approximation is going to be much closer. Do you agree? So let's do x1. Let's find y1. And then let's find area 1. You can see the difference is minimum because the more the grid, the larger the grid or the thinner the grid, the better the approximation. Now, there is a mathematical tool, guys, that makes much simpler our life and much better approximation. So I will not discuss about the technique, but it's called quadrature L of X and Y. You can see humps. I don't need to do that in my interval -1 and 2. Here I go. So this is the precise. Okay, it's faster because what it does, guys, is if it's flat, the length of the rectangle increases. If it's very peaky, the length of the rectangle decreases at the minimum. So you see, so this is an automatic process. So it's much more efficient than the trapezoidal method. Okay, so integrals, guys, is piece of cake. What is tricky is when we take derivatives. Okay, so now let's go again. Let's create again our x from 0, 0.1, and let's say to 1. So I create x. Let me check in the chat. I sent you one. Can you use the first one that I sent you? Hey, Ryan, thank you for letting me know about that. The recording, I completely forgot. This one is the first data set that I sent you in the chat. Can you recover that? Can you create a polyfit second degree, please? Evaluate the function and plot the function. Don't plot the function, let's plot together. So first do the polyfit second degree, evaluate the function and wait for me there. Let's graph this together just to show you what happens. So, okay, so we can do P. I think we do this polyfit XY. You agree? Oh. One,
X, Y, and 2. X,
Ah,
Y, comma 2.
yeah, that's completely right. I need to have the second. Wait, I have defined this correctly or not? 0, oh no, my X is wrong. It's 1 only. And my Y is correct. Now we have. So this is my polynomial, guys. Do you agree? So now what I will do is I will do a lean space just to make it a lean space like before, 0 to 1. So I have 100 observations there. And then I will do a Z that is going to be a polyval. I'm evaluating this function, P using X. Do you agree? So I have all the ingredients. So what I will do now, guys, is I will do a multiple plot. I will plot X and Y. I will call this perhaps something like that. I want X and Y, just the interpolation. Then I will want, stupid me. 1 second, guys. Cannot do this stuff. I'm tired already. So Y, my polynomial, I need to create, this one should be X1, just not to destroy the previous X. Not you. Polyval. P in X1. Okay, so now I can do the plot. I can plot X, comma, Y. I want to create these ones. I want to create an interpolation. And I want to create Xi with Z. And yeah, I can call this perhaps, and do this red. What is X? X is correct.
Professor, you never created an XI in this instance.
It's X1. Yikes. Now I got it. Thank you, Karen. Here we go. So the interpolation is the orange one, and my feet is my red one. Do you agree? Do you agree, guys? Okay, and so this is a smooth function. The red one, so my feet is a smooth function. Okay? So what we are going to do, guys, is we're going to take the derivative. This is called PD. It's going to be simply poly there of my function P. So this is my derivative. So what I do is I'm doing, guys, I'm taking the derivative, the first derivative of my function. Do you agree? And what I will do is I will create C1 and I will evaluate this one here, polyval, PD with my values of Xi, X1. Do you understand what I'm doing? So I have my function, I have fitted my function, so it's P, this function. I take the first derivative, this is my first derivative. And then what I will do is I will evaluate this derivative. I will create a graph of this derivative in this point here. And then I will simply plot. I will do a figure, okay? I don't want to destroy it. Figure and plot X1, C1. Do you see this one here? The derivative. Now, guys, have you recognized the function that I have drawn? Do you remember?
Can you go back for a second?
Yeah, but wait. Yes, I will go in a minute. I just want to give you the intuition of what I'm doing. 1 second. Nice, terrible graph. This is, guys, the example I have provided to you is a very simple example of a micro one. So you have a utility function, guys, that normally looks like a function that looks like that. So this is X, for example, and this is the utility of X, okay? So what is the logic of this? Imagine this is water. When you when you don't have water, guys, you're in the middle of desert, you value water a lot. Do you agree? Then you start drinking water. So the level of satisfaction of the first part of the first drops of water are extremely high. But as soon as you start drinking, there is a point in which, you know what, the utility becomes this utility. Do you agree? You cannot drink anymore. You can die of drinking too much water. So this is a utility function. Now, the way we evaluate utility function is using marginal utility function. So what is the marginal utility? Is simply the derivative of the utility. So if this is u of x, what we take is the derivative of u respect to x. And then, as you can see here, guys, when this is 0, the marginal utility is very high. Right? So let me move this one here. And you can see that when the derivative equals 0, because remember the derivative here equals 0, when the derivative equals 0, I start having this utility. So basically, this is my marginal, it should be a line. Looks like that. This is my marginal utility of x. Got it? So, and that's what we do, guys. What we do is basically, we are going to have a bunch of points, like the ones in my example. And what we try to do is we try to fit a line, try to fit a curve. And once we have this fitted curve, what we try to do is we try to create a marginal utility. Right? And it looks like that. This is what happens. Beautiful utility function. Right? And then you can do analysis. You know, what is your utility when you have 10 glasses of water? What's your utility when you have 100 glasses of water? So you're basically, you're on the negative side of the equation. This is what we're doing. Now, let's go to the MATLAB so you can take a look to the MATLAB function. Here we go.
Just a question on before we move on here. What exactly were the comments that we said before we did the last plot, the plot before this plot? We said x1 equals to 0 to 0.1 to 1, and then the y, and then p equals to polyfit x1, y2, and then x to link space 0, 1, right? Or because
always 0, 1, always 0, 1.
Yeah, I did exactly that and not plot. I was just wondering if you can rerun
which one
very quickly.
From where?
From plot. So yeah,
From
I got
here?
exact. Yeah, I did.
So this is the original data. What we do from the original data, I need to take the derivative.
Right. No. I was talking about the one above. Go above it. Like I got something. Vectors must be the same length.
Yes, because you know what's going to happen. So you do first. Okay, so let's start this one. I think it was, yeah, we start from 0. Okay.
Thank you.
Yeah, because I got so confused here. Let me move this one. Okay, so let's go with x. This is my x. Do you agree? Sorry. Now my x was, yeah, this was my x. Agree with me, guys? 0 to 0.1 to 1. Then I have my y. This is my y. Agree? Then what I did is I call z was equal to polyfit x, y, 2. So we have done the fit, and then we have said, okay, let's do x1. Now it's going to be from 0. Oh, no, we said it's going to be linear space just to have 100 observations from 0 to 1. You agree? So this is x1. And then I created, what was my, yeah. This one here is what I call P. Now I will create Z that is going to be a polyfit. C is not a polyfit. C is going to be this one here. Agree? So I have P, and C is going to be evaluated in X1. So this is my Z. So I have all the ingredients for the first graph. Then I will do the main graph. The main graph is this one here. XY is going to have a dot. XY, X1Z, X1 and Z is built here, and R. So here we go. This is the first graph. So this is basically what is correct. From here. Ignore this. It's not C. This is what I call P. And then we should have it. Do you have it? Guys, do you get this one?
Yep. No, I do.
Okay, perfect. And now what it's saying is once I have the fitted value, once I have the function that is a fitted function, then I can take the derivative. So basically what I'm doing is I'm computing the marginal utility of x. Okay, when you take the derivative, I call PD, I think something like that. Where's PD? PD. So it's the first derivative of my function. Then I said, oh, you know what? I will create C1. C1 is simply going to be polyad. I will evaluate in x1 values, PD. I didn't do that. I needed to do that. And once I have that, I have everything. So now I can do my plot, my simple plot, this one here. Where's my plot? This one here. So I'm plotting now the marginal utilities, right? You understand that, guys? And then you have your marginal utility. It looks like that. It looks beautiful.
We said Z1 to polyvet. What's the exact command again, just very quickly?
Which one?
No, never mind. Actually, I see on the right hand side polyvet. Yeah, polyval PDX1.
Yes. Okay. Now, guys, and you know, this comes in relation to what Shaw has mentioned to you, Philip Shaw mentioned to you, Kevin. So, you know what is the derivative of y? It's simply the difference between y divided by the difference of x, right? That's the mathematical definition of dy. So let me do this. dy equals diff of y divided by diff of x. So I'm taking the difference. The difference is simply taking this value minus this value minus this value. Okay? So these are the differences. And this is the technical definition also of a derivative. It's change on y divided by change on x. Do you agree? Now, let's define xd. I will define x is going to be, I think it's going to be 1 to length of x minus 1, just to make it conformal here. I think it will work. And then we can do the plot of xd dy. Oh, hopefully I haven't. Yeah, well, I destroyed. Do you remember the other one was a line, guys? Do you remember? If we use the dots, so if you use basically the elements here, these dots here, so taking the difference between dots, so basically what you're doing is you're doing an interpolation, right? When you take the diff, you're basically assuming an interpolation from dot to dot. Then you're done. You have so many kinks, and take a look to the, well, I deleted the other one, but the other one was a smooth function. This is the function that if you use the non-smoothed function. This one here corresponds to using the orange one. And that's what I was telling to you guys. Normally when you do research, guys, you first try to smooth the function. Once you have a smoothed function, so you fit the function, it's a smooth function, then you can take the derivative. And you work with that derivative. Okay? Otherwise, it is extremely messy, guys. You cannot have anything here. There is no useful information on this one. Okay? I think that we can stop here. I ran a lot, but this was good. Please read, review, and try to do this by yourself. Study the code that I gave you. I gave you everything. Okay, study the code and try to understand, etc. So this is the first assignment for you guys, and the second assignment for you is going to be, I send you a bunch of photocopies. Have you seen? I send you a bunch of photocopies. Can you please read them? Okay, just read them. Just try to make sense of what they are talking about, because one is marginal utility, marginal cost, etc. Just read and just understand the logic of the economics. They are very simple economic models that we're going to start dealing with on our next class on Monday. Okay, guys? Study, do the computer solution number 6, the homework number 6. That is a really cool one. Okay, you're going to learn how to do polynomials, how to divide the data, how to organize the data, find season trends, etc. It's really cool. Just do it step by step. You have all the tools to do that. And if you have questions, just ask me. You can send me an email. Hey, Professor, I don't understand this part here. I can guide you. Make sense? Okay, guys. So we see you in a couple, well, 4 or 5 days.
Yeah, Professor, a word.
See you guys. Take care. Okay.
Thank you, Professor.
See you guys. Take care. Good night. Take
Thank
care.
you. Have a good night.
Good night.
Prof.
Yes. Let me